All right, welcome. And first things first. Great job on test number 1. Just having done it, that's a great job. I have not looked them over yet, so remember, for quizzes and the tests, I do look through them. I also had quite a few people message about assignment 3, so I will go through assignment 3 because these assignments drive me nuts. But so I'll go through assignment 3. But if you are looking at assignments, I don't go through the assignments. So if you find something that should be correct but is marked incorrect, then just send me an email and I'll fix it on kind of a case-by-case basis. Okay, and so test 1 done. Now I'll tell you a secret, I guess. Now we get to start the fun stuff. So today we'll still have a little bit of kind of core math to get through. We're going to talk about exponents and logarithms because we'll need those sort of. We'll need to have an understanding of them at least, and then we'll get into simple interest next week. Okay. Let me see here. How come? It's not working. Oh, it doesn't matter. Yeah. So I got a direct message. There was a problem in assignment 3 in a question which had 4 parts in it. I'll wait for the follow-up, the question there. But yeah, so I know for assignment 3, I will go through assignment 3. I haven't done it yet though. Okay, and so I will, meaning I haven't done it yet. Okay. So in terms of showing your work, all you're doing is, if you feel comfortable with the answer that you've given, then that's totally fine. But I look at your written work, so it's not for marks, but if I can look at your written work and see that, okay, well, what you did made sense, right? And so then I can give you part marks. Right. Whereas if you haven't written it down, then I can't give you part marks. Right. But if you're okay with that, then that's totally fine. And so it just depends on, how sure you want to be about your part marks. Right. In case you enter the wrong answer or something like that. Right. And then I can go back and look and just make sure it makes sense. And then I can give you marks. Right. Because that's what's hard about an online test, right? Is there are no part marks, and so it makes it harder. So I want to be able to give you part marks at least. Oh, nice, yeah. And for this test, I feel like you had a lot of time to do it, so you were able to show all your work, right? I think as we kind of get through the material, right, you'll pick up on what you need to write down and maybe things that you can just kind of skip to the answer for. But it's always safest to just write everything down. Awesome. Okay, so I will go through assignment 3 and test number 1 and make adjustments, right? Kind of when it's marking weird. Let me just see if I can fix something. I knew it. It's on the wrong camera. They're very similar though. This one's got like a glam light on it though. Vanity and sanity. All right. So test 1 done. And yeah, test one always feels like kind of a hodgepodge of just things that we've learned, and things will really calm down for test two. And we just need to get through this first section of chapter 4, which is also the first part of part 3. So part 3 of the textbook is called Simple and Compound Interest. Ditch this. So we're going to start with simple interest and then quickly move into compound interest, which is more relevant, right? Whenever we're talking about kind of car loans or mortgages or anything like that, then we're talking about compound interest. Simple interest is very rare, but we use it to introduce all the scenarios. And then we just slowly build, we just kind of snowball out into more complex interest problems. Okay? And so for today, what we're going to do is we're just going to talk about, so section 4.1 is called the basics, which I feel like so Joe wrote the book and he's the chair of our department right now. And I feel like he calls every first section the basics, which isn't very helpful, or I guess it's the basics. But so what I'm going to say is I'm going to clarify that exponents and logarithms in this basics section. Okay. And I just realized, okay, good. That one's fine. All right. So today, just kind of more math, just ironing out the details. So exponents and logarithms, you're probably familiar with. So hopefully it's just a nice review. But there are exponent laws and log laws. And after today, I expect you to have them memorized or have them written down and to be able to apply them. Okay. So first, we'll start with exponents. I don't know why I can't write today. I'm sitting. Exponents, right? Which are really just powers, if you prefer to call them powers, but technically exponents. Okay, so if you have something like a times a times a times a, right, all the way up, you can multiply n a's together, n a's multiplied together. You would write it as a to the power of n. Okay. A is called the base, okay? And n is the exponent or the power. Okay? So where a, oops. So in a to the power of n, so a is the base, and n is the power or exponent. Oops, exponent, singular. Okay. Hopefully so far so good. Okay. All right, so we can do things like easy breezy here. For example, if I have 5 times 5 times 5 times 5, that's going to be 5, right? The base to the power of however many times I'm multiplying it, which in this case is 4, 5 to the power of 4. Okay. Our calculator can do that, right? So usually we just don't feel like multiplying 5 by 5 by 5 by 5. So then we just use the 5 to the power of 4. Okay. On our calculator, or the one that I'm using at least, which is the downside here. That BA Calc. Okay. There's a button. I'll take a screenshot here. So here, just so we have it. You're going to use this button. How can I highlight this button? So you put the base on the screen. So to calculate 5 to the power of 4. And if this feels obvious, then that's totally fine. But I do get questions about this. So that's why I want to go through it as we're introducing things. Okay, because otherwise it's too confusing and I don't want to leave anyone behind. So to calculate 5 to the power of 4 on your calculator, right, this one in particular, the first thing you're going to do is enter 5. Oops. Obviously. But, and then y to the power of x, copy. And then the power. Okay. So first the base, or maybe I'll use the same colors, haha, as I did before. Right, first the base and then the power. And then enter, okay? Because if we try it, let's see here. Oh boy, I don't want that. 5 to the power of 4. It's not going to show us the answer until we hit equals 625. Okay. Which you could try, right? 5 times 5 times 5 times 5 equals 625. Hopefully everyone's convinced. And then hit the equal button. Oh, nice. So that's how you're going to find those powers. If you only want to the power of 2 specifically, there is an x to the power of 2 button, right? So if you want 5 to the power of 2, then you would just do 5 and then x to the 2 and then equals, and it would just do it for you, right? But it doesn't matter. What if I want you to write out 2 to the power of 5? Right. Then what I'm saying is I want to do 2 times 2 times 2 times 2 5 times. Right, I lost track. Okay, so here 2 times 2 times 2 times 2, 1, 2, 3, 4 times 2. Okay. So you need to be able to kind of, I guess I think of it as an accordion, right? Accordion it up into a power or expand it into just a multiplication. Okay. So let's talk about rules of exponents. Rules of exponents. And these are on page 92 of your textbook. Just in case you get lost somewhere, then they are on page 92, so should be okay. And before we can establish some of these rules, we need to have some assumptions clarified here. And so first thing I'm going to say is I'm going to let a be greater than 0. Okay. A is going to be representing the base. And so the base has to be positive, right? So I'm not going to be talking about a negative base. Okay. And if you're familiar with exponents, right, then even exponents on a negative base give you positive values, but odd exponents give you negative values. So that's why I'm just going to force it to be positive. Okay. So we're going to let a be greater than 0, which means the base must be a non-zero, right? Because it has to be greater than 0, not equal to 0, non-zero positive number. And the next thing I'm going to say is that m and n, which are going to be the powers that we're going to use, are in the set of real numbers. Okay, don't worry about this notation. It's just shorthand, and I am going to write it out. Okay, but here, this is in the set of real numbers. And I'll clarify what that means. Okay. So here, M and N, okay, are any number between negative infinity and infinity. Okay. So a real number is just any number between negative infinity and positive infinity. So any number that you can possibly think of. And that's all it's saying, right? M and N can be anything, right? Except imaginary numbers, if you're familiar with that. But don't worry about that. Okay. All right. So the first rule is one that we've already established. Okay, and so that is that a to the power of n is the same as a times a times a all the way up to a, and of course n times. Okay. So a multiplied n times is what a to the power of n means. Okay. That's not so much a rule, I guess, is just fact. But the second one is a new rule that we're going to introduce, and we're going to use this quite a bit. In fact, we already used it in, I think, chapter 2 or something when we were trying to simplify. And so I've already briefly introduced it, but here it is in the flesh. A to the power of m times a to the power of n. Okay. Notice I have the same base. And so what can I do? I can combine that base and I can simplify. And what happens is if I'm multiplying the same base, I can use that base and add the exponents. Okay. So here I'll write that. So if multiplying exponents of the same base we can simplify by adding the exponents. So there's a link there, right? If you're multiplying the bases, then you add the exponents. Mm-hmm. Similarly, if you have divisions, so of the same base, a to the power of m over a to the power of n is going to be the same as a to the m minus n. Okay? And so now the only thing that changes here are two things that change, right? If we're dividing exponents of the same base, we can simplify by subtracting the numerator exponent, no, the denominator exponent from the numerator exponent. Okay, so if dividing exponents of the same base, we can simplify by subtracting, oops, the denominator exponent exponent from the numerator exponent. Very wordy, right? And so here, that's why we use this notation. I'm just writing out what it means, right, in words, but in the end, we're just going to rely on these rules, right? Because reading this is tough, right? But I'm just trying to lay it out so that you can go back to it and have a little crutch if you need it. Okay, we can simplify by subtracting the denominator exponent from the numerator exponent. No? All right. Another rule. What if I have a to the power of m in brackets, and then that's to the power of n? Okay. I do just bring in that n and I multiply the powers. Okay. And so here, this becomes a to the power of m times n. Okay. This is just an extension of rule number 1. Okay, so what does a to the power of m look like, right? I could just use it as a base and do it to the power of n, but then in each one, I'm going to have m a's as well, right? And so here, what this looks like, or maybe I'll just write it out. This is an extension of rule number 1. Okay. How? If I use a to the power of m as the base, and I do it n times, right? Each one of these is going to expand by m, right? A to the power of m becomes a times a times a times a, m times, and then I do that n times, and so it's the same. I just think of it as expanding, and so I'm just multiplying these powers because there's only one base, and so they multiply together. Fifth rule, a times b in brackets to the power of m. Okay. So what I can do is exactly the same thing that I did before, because I'm multiplying, and also it applies to division as well, but because I'm multiplying, I'm allowed to bring that m inside. So I'm allowed to expand it onto each of the bases inside. So a to the power of m times b to the power of m. So here, if multiplying, two bases, the exponent expands into inside the brackets, right? Or expands, yeah, I guess into the brackets. Expanding gets rid of the brackets, but anyways, so if multiplying two bases, the exponent expands onto both bases. Okay. has to be multiplying or division, which I have a feeling it's on my next page here. It's the next one. Okay. It is rule number 6. If I have a over b all to the power of m, okay, so now I have a fraction here or division inside, I can do the same thing because I'm able to bring that m inside onto each of the bases. So I got a to the power of m over b to the power of m. Okay, and this is just an extension. Or maybe, you know what? I'm going to copy this because it's the same. The only thing that's changed is the division. So if dividing two bases, right, a and b, then the exponent expands onto both bases, right? A to the m, b to the m. Okay, notice that a and b are not the same base, right? And so we cannot use something like this, right, where we simplified a to the m over a to the n, right? Then I can simplify, but it has to be the same base, whereas now I have a different base, so I can't do that. Okay, there's all these rules, and the more you use them, they'll just become second nature, right? Anything to the power of 0, I should make that look like a 0, is 1. Okay, so that's just kind of a fun fact. Okay, and so fact, it's not really a rule or anything. I guess it is a rule, it's a fact. Anything to the power of 0 is 1. Right? You could have 4 million to the power of 0 and it would be 1. How about rule number 8? So now we're going to get into dealing with these negative powers. So if I have a to the negative n, that's going to be the same as 1 over a to the n. Okay, so that negative power, right, or negative exponent actually places it down in the denominator. Okay, and so let's see here. This, we can kind of see it in that rule where we had the same base, so a to the power of m in the numerator, and then a over a to the n, and then it was subtraction, and it's because of this, right? So they're all interlinked. Okay, and so a negative exponent moves the base and the exponent into the denominator, or vice versa. So we use this a lot. So a negative exponent moves the base and exponent into the, and maybe just say positive exponent into the denominator. We use this a lot. And just as a heads up, and I do have examples, but we need to go through all the rules first, and then we can do examples, okay? Because we're gonna kind of pick and choose and figure out how to simplify things. Okay, so kind of in the same realm is if I have an exponent that is a fraction, that's the same as the nth root of a. Okay, so we can rewrite we can rewrite the nth root as a power is usually the direction that we move it to. Okay, so if I want to take the fourth root of something, we all know there's no fourth root button. And so what do you have to do? You have to use 1/4 as your exponent instead. And totally work. That's how you would use your calculator to do it. Okay. Guess I didn't. We can rewrite the nth root as a power. Using 1/n as the exponent. And then finally, the last one is that a to the power of m/n. So now I have an exponent, which is a fraction, but also there's the m in there. So how does that work? Okay, I can rewrite this as a to the power of m to the power of 1/n. Okay, and this is by rule number 4. Okay, where I can split up the m/n as m times 1/n. That's still true, right? And so now if I can split those exponents into a multiplication, then I can rewrite this, right? And so now if I have a base, which happens to be also an exponent, right? a to the power of n, then I can take the nth root of that and I can get to the nth root of a to the power of m, and this is an extension of rule number 9. Okay. So those are the rules, and because you're working online, because it's open book, right? You need to have these handy somewhere until they become second nature, right? Until you have them memorized and you can just use them and apply them, right? You'll need to refer to them and just make sure that what you're doing is legal, right? Legal in a math sense. Okay, there's lots of illegal math that you could be doing, but we want to steer clear. All right, so if I want to simplify something like a to the power of 4 times a to the power of 8 divided by a to the power of 7. First thing I'm going to note is that I have all the same bases, right? And so that means that I should be able to rewrite this in terms of just a to the power of 1 exponent, but I need to simplify it first. Okay. And maybe what I'll do is I'm gonna start this on a fresh page, because what I want to do is I am going to go through and simplify this, but at each step I'm going to tell you which rule I'm applying. Okay, and it seems to be a little bit laggy today, so because I have the steps here, I'm not going to scroll back and forth so much, okay, unless I'm going to try not to. Okay, so I want to simplify. Let's use a different color here. So I'm going to start with a to the power of 4 times a to the power of 8 divided by a to the power of 7. Okay. First thing we notice is these are all the same base. Okay. So what we can do, or let's use this color. I'm going to start by simplifying the numerator. Now, there are many ways that you could go about and solve this problem. Okay, so just because I do it one way, as long as you end up at the same answer, then you probably did it correctly, right? And as long as you can tell me which rules you applied, there's many different orders that you can do it. Okay. In fact, maybe what we'll do is we'll simplify it two ways, right? There are many ways to solve it. First way I'm going to do it is I'm going to simplify the numerator first. Okay, if I'm multiplying the same base, then by rule number 2, I can add the powers, right? And so this becomes a to the power of 4 plus 8 by rule number 2, divided by a to the power of 7. Okay. So a to the power of 4 plus 8 is 12, divided by a to the power of 7. So now what I'm going to do is, because these are the same base, right, then it's going to be beneficial for me to move this base up top. And how do I do that? I can do that by negating the 7, right? And so here, this becomes a to the power of 12 times a to the negative 7. Okay. Let's see here. It's either by rule number 8 or rule number 3. Now let's compare those two. Right. Rule number 8 says that, okay, if I have something in the denominator, right, then I can bring it up top, right, basically to the numerator by negating the power. That's what I did. And so, or if we want to think about it in terms of rule number 3, that would speed things up a little bit, right? Because I do have this scenario, right? M is 12 in this case, and N is 7 in this case. So I could rewrite it as just immediately a to the power of 12 minus 7. Okay, but I didn't do that. I showed the step where I brought it upstairs. But that's where this comes from, right? Because we have the same base now, right? I would be using this property, right, where m is 12 and n is negative 7. So then n a to the power of 12 minus 7, right? And so they're all interlinked, and we need to just get to know them. Okay. So this becomes a to the power of 12 minus 7 by rule number 2. Okay. Just as a side note, when you are practicing your simplification, you don't have to say what rule you're using, but I think it would be really helpful in the beginning, at least, if you're not feeling very comfortable yet, right, then you can kind of support your statements with these rules, and you can go back and make sure that they make sense. But what we get in the end is we get a to the power of 5. Okay. So that was one way that we can simplify this. Okay. I want to show you a different route that we could take. I mean, we're going to end up at the same answer, so it doesn't really matter, right? I just want to show you that there are many ways that you can massage this into a to the power of 5. Okay. Another way we could simplify is if I have a to the power of 4 times a to the power of 8 divided by a to the power of 7. Another thing I could do is I could just bring this a to the power of 7 upstairs immediately. Okay. And so that's how I think about it. I bring it upstairs, I bring it to the numerator by negating that power. And so this becomes a to the power of 4. And I'm going to not use the multiplier here because it should be obvious, times a to the power of 8 times a to the negative 7. And this is by rule number 2, or sorry, rule number 8, I guess. By rule number 8. And I can bring this from the numerator upstairs. Notice now I'm multiplying the same base. And so it doesn't matter how many times you multiply, as long as you have the same base, you can add the exponents. Okay. And so this becomes a to the power of 4 plus 8 minus, and technically it's plus minus 7. Okay. Usually we don't write that. We just write minus 7, but technically it is plus minus 7. And that's how subtraction works, right? You're not actually, subtraction is just a special case of addition where you're adding a negative number. Okay. And so by rule number 2, okay, 4 plus 8 minus 7 puts us back at a to the power of 5. Okay. Nice. Let's do another example. We're going to simplify.
Professor.
Yes.
Sorry to interrupt you, but
That's
the electricity went out on the campus.
Oh, wow.
So, well, I don't know how much I'm gonna stand without the internet. So just to let you know.
Quite all right. You'll be able to watch the video after.
I mean, we're still okay, and I have battery, but I don't know the internet how long it's gonna stand.
That's crazy. Yeah, I see it's all dark.
Yes. Yes. So everybody's like, I don't know.
Yeah.
So is
everyone just working in the dark?
Yes. Just to let you know.
That's quite all right.
Okay.
Okay, good. We're going to simplify 1 plus I, and 1 plus I to the power of 3 times 1 plus I to the power of 9 divided by 1 plus I to the power of 6. Let's see here. I'll just leave that there. Okay, let's see here. So one thing that I want you to notice is that although it might be tempting to expand and then simplify, that would make a real mess. Okay, and I'll show you why. But for these, right, when we have these nice same bases, right, then I would leverage that, right? If you don't want to expand those brackets, which you really don't want to do, okay? So here, notice that these are all the same base of 1 plus I. Okay, so you don't expand, so do not expand. Okay. So let's see here. Why don't we expand? Right? It might be tempting to say, okay, well, I can just bring in this 3 inside, but the exponent laws, remember, only, and now I am going to scroll back here despite the lag. Okay. You're only allowed to pull in the power or the exponent if you're multiplying or dividing inside. So it does not apply for addition and subtraction inside. Okay. And so here, I'm going to make a note. Okay. We can only bring the power inside the brackets if we are multiplying or dividing inside. Okay. But because here we have 1 plus I, right? Then I have addition or subtraction, right? And so then I can't do it. So one thing that we're going to notice, okay, so note what I mean is that 1 plus I to the power of 3 is not equal to 1 to the 3 plus I to the 3. Okay, that's not true. Okay, because what does 1 plus I to the power of 3, what does that mean? Right? 1 plus I to the power of 3 is 1 plus I times 1 plus I times 1 plus I. Right? And so that's by rule number 1. It's probably the only one I've memorized. The rule number 1. Okay, so what would you have to do here? You can expand this, right? And so here, right, you would have to take 1 times 1 times and 1 times I, and then I times 1, and then I times I. Let's do it. Right, this would become 1 times I, so that's I. Sorry, I jumped ahead. 1 times 1 plus 1 times I plus I times 1 is I plus I times I, which is I squared. Aha, finally we get to use our exponent rules. Times 1 plus I. So notice how I expand 2 sets of brackets at a time, right? So I'm still using that. I guess it's FOIL, but I never call it that. And so I can simplify, I can collect like terms here, and I have 2I in the center. And so I can simplify that first. So I get 1 plus 2I plus I squared times 1 plus I. Now I can expand these brackets. 1 times 1 is 1. 1 times I is I, plus 2I times 1 is 2I, plus 2I times I is 2I squared, plus I squared times 1 is I squared, plus I squared times I, which is I to the 3. If I simplify, if I collect like terms here, I get 1 plus 3I plus 3I squared plus I to the 3. Okay. Notice that this is not, right? This is not 1 to the 3 plus I to the 3, right? And so here, notice this is not the same as 1 to the 3 plus I to the 3. Okay. And so this is not true. It's what we would call illegal math. So if you felt like expanding these, right, 1 plus I to the power of 3, you would end up here. Where's what's the problem, right? 3 was the lowest power that we would have had to deal with. Now 9, that's 1 plus I times 1 plus I plus 1 plus I times 1 plus I 9 times, right? So you can imagine what a mess that would make. So you do not want to expand these, right? You want to treat 1 plus I as the base. Okay. Okay. So what can we do? We can simplify. So let's go back to the problem, right? So if we want to simplify 1 plus I to the, and maybe I'll start on a fresh line here. 1 plus I to the power of 3 times 1 plus I to the power of 9 times 1, or divided by 1 plus I to the power of 6. Okay. couple of ways you could do it, right? Same thing, as long as you treat 1 plus I as the base, right? It doesn't matter. Then you're just dealing with these exponents. But a couple of ways we could do it, right? And kind of the more practice that you have, you'll be able to do them all in kind of one go, right? So what would one go be here, right? I would do 3 plus 9 and then minus 6. Okay. So this becomes 1 plus I to the power of 3 plus 9 divided by 1 plus I to the power of 6, which is 1 plus I. Yeah, good. So now 1 plus I to the power of 12 times 1 plus I to the negative 6. 1 plus I to the power of 6. Skipping us, so I didn't write out every step, right? I should have written 12 minus 6 or 12 plus negative 6, but I didn't because I just knew what the answer was, right? And you're allowed to do that, right? There's you don't have to write out every step as we get more comfortable. Okay. And so what were the rules that I used here? This first one was rule number 2. This was rule number 8. And this was rule number 2, I think, right? Where, yeah, A over, yeah. I think. Can't remember what rule number 2 was. Yeah, that's fine. Good. All right. Let's do another example. Okay. So we're going to simplify bracket x plus 3 to the 5 divided by, or bracket 3 over 2 in the exponent. Okay, I'll clean that up. I'll give you guys just a minute to work through that, massage it with the exponent laws. Okay. Even if you're not quite finished, that's okay. We'll get started plugging away on this. All right, so I'm going to rewrite it here, x plus 3 to the power of 5, and then that's to the power of 3 over 2. Okay. And so now what I'm going to do is I can use, I guess it's rule number 4, burning my brain. I know, but we'll get there. We'll get there. Okay, so first I'm going to use the fact that if I have 2 exponents being multiplied together like this, then I can just simplify it by removing these brackets. So that's the first thing that I'm going to do. So I'm going to have x plus 3 still in the brackets, and then 5 times 3 over 2. And this is by rule number 4. Okay, good. So now 5 times 3 is 15, then divided by 2. So I'm just going to simplify that here. X plus 3 to the power of 15 divided by 2. And that's just simplifying that fraction. Now, when I have 2 in the denominator of the power, then that becomes a square root of everything that it's the power of. Okay? And so I can rewrite this as x plus 3 to the power of 15 to the power, or yeah, to the power of 1 over 2, if you want to. You don't have to, right? But it might help clarify what's about to happen next. You won't believe what happens next. Okay, so this, right, power of 1/2 means that I'm taking the square root of everything inside. So the square root, we usually don't put a little 2 in here, right? But I'll do it for now, right? But the square root is one of those special roots where you don't have to clarify. And so it's the square root of x plus 3 to the power of 15. Okay. And that's by rule number 10, that last rule that we established. Okay. Is it only rule number 10? Let me go back to my rules. And 9. I mean, technically by, yeah, I guess rule number 10. I'll say or number 9 if you prefer. They all kind of go together. Okay. One thing to note here. Usually the square root does not require, writing a 2 in the hook. I call it the hook of the root. Require writing a 2 in the hook. I actually don't know why I call it the hook, right? We usually just write the square root. Okay. For any other root, we write the root number in the hook. Right. So for example, that is if I want to have the third root of x, right? Wait, need to clean that up a little bit. And that's the third root of x. Okay. It's not wrong if you write the 2 in there, right? But usually we're not used to seeing the 2 in there, so that's why I wanted to clarify. Okay. So this would be the same as x to the 1 over 3, or x to the 1 over 4 would be written as the fourth root of x. Right, so just be able to move back and forth like that. Okay. Now, roots, you might remember as we can use the roots to essentially undo powers. Okay, so if you have x to the power of 3, then if you take the third root of x to the power of 3, you end up with just x, right? So if you're trying to solve for x, then you have to, and it has a power on it, then you need to use a root, right? And you just use the root of whatever the power is. Okay. And so we use roots to, let's say, undo powers. Right, so for example, if we want to solve for x, if you have x to the power of 5, oops. If I want to solve for x, what I'm going to have to do is I'm going to have to take the fifth root of x to the power of 5. Now, usually there's an equation. So to simplify things a little bit for us to look at, I'm going to solve x to the power of 5 is, sure, 243. I don't know, some number, doesn't matter. Okay, so if I want to solve for x here, then I need to get x on its own, right? And so I need to get rid of that fifth power. And the only way to do that is to take the fifth root of both sides, right? What I do to one side, I have to do to the other side. Okay? And so this becomes, so I need to take the fifth root of x to the power of 5 is the same as the fifth root of 243, right? I need to take, so here, take the fifth root of both sides. I usually don't show why it works, okay, but I will do it this time, okay, but usually in my work, it's understood that, okay, we've established that this cancels those powers. You still have this fifth root on 243, of course, that you have to deal with now, okay, but right, why this works is because you have x to the power of 5 and to the power of 1 over 5, right? If you rewrite that root as a power, okay? And so, okay, but 5 times 1 over 5 just becomes 5 over 5, right? And so this becomes x to the power of 5 over 5. But 5 over 5 is just 1. So x to the power of 1, but x to the power of 1 is just x. Okay. And so that's why it works. Okay. You're still stuck with this fifth root of 243, but how are you going to use your calculator to solve that? So x is 243 to the power of 1 over 5, right? If you rewrite this, then you can use your calculator. Okay, 243 to the power of 1 over 5. Let's practice on our calculator here. Can I close it, or is it a decoy? Okay. All right. So I want to do 243 to the power of 1 over 5. So what I'm going to do is I'm going to put in 243. That's my base, right? And then I want that to the power of 1 over 5. Now, just so I don't do 243 to the power of 1 and then take that value and divide it by 5, I'm going to use the brackets around 1 over 5. Okay, so I'm going to use the y to the x button. And then it doesn't change anything on the screen. So it's kind of a it's a fancy calculator, but it's not very fancy to look at. Okay, but what I'm going to do is I'm going to use a bracket. So I'm going to use the right hand bracket. Okay, and I'm going to do 1 divided by 5 and then close that bracket. Okay, 1 over 5 is 0.2, but once I hit equals, then it'll give me that answer. and that answer is 3. I can double check this by taking 243 to the power of 0.2, and it's still 3. Okay. Nice. So that's good. So 243, the fifth root of 243 is just 3. Wow. Okay. Let's do another example. I want you to solve y squared equals x squared minus y squared for y. Okay. And I do want to give you just a couple of minutes to try to work through that on your own before we do it together. Okay. So first thing I'm going to do is I'm going to rewrite this on a fresh line here. So I have xy squared is equal to x squared minus y squared. So again, there are a few different ways that you could solve this properly and still be safe, right? And so for me, what I'm going to do is, because I want to solve for y, I'm going to move my y's over to the left-hand side. So to do that, I need to add y squared to both sides. So I get xy squared plus y squared equals x squared. Okay. And so here, right, just to clarify, I move the y's to one side. Then what I'm going to do is I have this common y squared. So y squared plus y squared, I can extract that, right? So factor out the y squared. So I get y squared times x plus 1 is equal to x squared. So I'm going to factor out the common y squared. Okay, so far so good. I'm seeing that I'm able to get y and y squared on its own, right? So the next thing I have to do is I have to divide both sides by x plus 1. And so I get y squared is x squared over x plus 1. I'm going to keep the brackets on there, just I don't need them, right? Because they're not doing anything, but just to emphasize that I just brought it over. Okay. And so now, right, what did I do? I divide, so I get y on its own. Now finally, or sorry, get y squared on its own. But I want to solve for y, not y squared. So now what do I have to do? I have to take the square root of both sides. And so this becomes y is the square root of everything inside, x squared over x plus 1. Okay. So here, take the square root of both sides to solve for y. Now here's the tricky part. Because I took the square root, okay, there's actually a positive and a negative side of the square root. Okay, so just as a note, okay, and maybe I'll do it in pink so it's not so extreme. Okay, and so here, this is what I want to make a note about. So it's actually the plus minus of that square root. Okay, and so and the only reason for that is because you can square it, and in either way you get a positive value, right? You can square a negative value and it becomes positive. You can square a positive value, it stays positive, right? And so we need to consider both sides. And so when we take the square root we need to consider both positive and negative values, positive and negative values of y. Okay. Which just means that therefore we need to add plus minus in front of the square root. Okay. So here, I would say this is simplified. I'm happy with this answer. Okay, and so we could keep going if we wanted to, right? If we wanted to keep working with our exponent rules. So let's just do that as an exercise. So I consider y equal to plus minus the square root of x squared over x plus 1 to be simplified. But we could keep going if we want to. We could keep simplifying, I guess. Simplifying for practice, let's say. So here, right, just to rewrite it, y is the plus minus square root of x squared over x plus 1. Okay. I can rewrite the square root as a power, right? And so then y is equal to, in fact, I'm not going to write the y because I want you to get in the habit of, if nothing's changing, then you just need to stack the equal signs, okay, until something does change. And so this is the plus minus of x squared over x plus 1 to the power of 1/2. Notice that the square root has that whole fraction inside, so then everything is wrapped up in that power. Okay. And this is by rule number 9, in case you're interested. Okay. And what else? What's the next thing I could do? So now, because I am multiplying and dividing, as long as I keep x plus 1 as one base, right, I can bring this exponent inside. And so I could write plus minus x squared times 1 over 2 over x plus 1 to the power of 1 over 2. And that's by rule number 6. And the only thing that I can simplify, well, I can rewrite this denominator as a square root if that looks nice to you. And then 2 divided by 2 is just 1. So then where I'm kind of stuck now and finally simplified is that x over x plus 1, but under the square root. Nice. Okay, good. So when we talk about exponents, right, we can talk about, right, it makes us think of kind of exponential growth. Now, exponential growth is when we have things like when we have the variable in the power. Okay, and so I'll start on a fresh page because it's kind of a new concept. Okay, so we often talk about, or hear about rather, exponential growth. Right? If we're talking about our money growing exponentially, then it's a good thing, and we know that, right? But if it's a spread of a disease growing exponentially, then we know it's a bad thing. And the reason that we know that is because we might not be familiar with the graph itself, but exponential growth, and we can visualize it as something like this. So you've got your x and your y. Okay. And maybe let's just specify that the x-axis is time, right? And maybe I'll keep the x here. So exponential growth would look something like this. Oh, nice. It cleaned it up. Okay. And so here, exponential growth is slow to start, right? So if y is the output, so maybe it's your income or something like that, right? So it's kind of slow to start, right? So it's increasing, but not very quickly. And then as the time increases, right? So as x gets larger, then all of a sudden, right? If this is the amount of money I bring in, then I'm very happy, right? But it's this exponential growth, okay? And so exponential growth is slow to start, but grows faster and faster with time. Yeah. Okay. So related to exponential growth is if we have things like the x variable in the power. Okay, so far our bases have been x's or a's or b's or whatever, but all our powers have been real numbers, right? And so now we're talking about variables. And so kind of as a transition, okay, so this might be something like, let's say 2 to the power of x. Okay? And we can graph it using Desmos if we want to. So if I have 2 to the power of x, right, this would be exponential growth. Okay, and I can grab this little dot, and I thought I could move it, right? And so I can see that as my x is only increasing a little bit, then my y is increasing quite a bit and very quickly, okay? And so here, right, this might be something like 2 to the power of x, right, would be that graph. Okay. So now notice that x is in the power. Okay. So now x, yeah, x is in the power. So just as kind of a segue, I guess, we know to solve for x in x to the power of 7, we just said that, okay, to solve for x here, I'm going to take the 7th root of x. We take the 7th root of x to the 7. Okay. What if we need to solve 7 to the power of x for x? Okay, so now here, right, now x is in the power. We don't have rules for that yet. Okay, so in order to solve this type of problem, we need logarithms. Okay, so exponents and logs, they always go together, and here we are. Okay. And so here, what I'm going to say is, I'm going to box this up. To solve this, we need logarithms, which is the next thing we want to talk about. So I did my undergrad is in math, and then my master's is in statistics. So, but when I was doing my undergrad, I told my grandpa, oh yeah, and he's like, oh yeah, what are you working on? Logarithms? Because logarithms in the past were very difficult, right? And so now our calculator just finds the logarithms of anything that we want. And so it's really easy. And so at the time, I didn't really understand what he was asking. But now I know that in the past, it was very difficult to solve logarithms. Okay, and so that's why we need to know these log laws, which is fun to say, hard to say, but fun to say. Okay, and so just to introduce logarithms, okay, if we need to solve for a value in the exponent, we will need to use logarithms. Okay. When we talk about logs, we talk about logs of different bases. Okay, there are two common ones, log base 10 and log base e. Okay, and so we will be working exclusively in log base e, the natural log. Okay, and so logarithms can have any base. Most commonly base 10 or base e. Now, e is one of those special numbers, just like pi, It's kind of like the lesser known irrational number, but it is 2.71828. There's a song, 2.71828. Okay. You don't have to remember it. I'll show you on your calculator. Oh, okay. How do I? What was that? Okay. So on your calculator, to find E, now I have to remember where E is. Oh, there it is. Over the LN button. So over on the left-hand side, it's in the yellow. So how you get to E is you have to hit the second and then E to the X. Now what it does is it needs to have the power on the screen. So E to the power of 0, we know is 1 because that's a fact, right? Anything to the power of 0 is 1. So if I change that, so to show 1 on the screen and then use E, second E, then I get what E is, 2.718281828. And then I think it changes because it's one of those irrational numbers. Okay, so, all right, to find E on your calculator, let's see here. Oh, how do I? This is the one I wanted to. So to use there, or yeah. To calculate E to the power of 4, for example, or E to the power of 1, let's do that on your calculator. You're going to have 1 on the screen. And then second. And then the ln, which has the E to the X, right? And then equals, of course. Yeah. And E. So this is just E, which would show you that 2.71828, blah, 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 blah. Okay. And so we're also going to be using this LN button quite a bit. Okay. Now, as a note, and I'm pretty sure that it goes for any business application. Same with statistics. We only work in base E. And so so whenever I say log, I actually mean log base E, which is called the natural log. I'll write that all down. But in business too, I think you only work in base E. It's only things like electricity and so physics, they work in log base 10. And computer science works in log base 2, but ignore those guys. All right, so for us, right, we will work exclusively in log base E, which we write log base E. Okay. Which is also called the natural logarithm, which is also called the natural logarithm. And is denoted by just ln. I tend to write it with a little kind of flair, and that's just so that, because that's how my brain recognizes that it's ln. Otherwise, this might look like 1n to me. And so just find a way to just trigger your brain to recognize that, okay, that's a log, or the natural log. But from here on out, when I say log, you say how high. No, when I say log, I mean the natural log. Okay. And so, right, I often say log, but mean natural log. Right. In high school, I know people call it ln, but that's not, I'm not going to say that. Right. I just call it the log. It's the only log that we're going to use, so it's not going to be conflicting or anything. Okay. So just like we did for exponents, we're going to develop some log laws. Fun to say. It's hard to say, but it's fun to say. And if you've seen Arrested Development, right, it makes you think of blah blah blah. It's log. But anyway, so log laws. So all of the log laws that we're going to develop here apply to any log. So log base 10, log base e, log base 2, it doesn't matter. But we're going to work exclusively in the natural log. So I'm only going to develop them for the natural log. But they apply, so the rules are the same for any log. Okay. So all of the logs, all of the log laws, oops, logs. We develop here apply to any base. Okay. But I will only write ln, natural log. Okay, so log laws, here we go. I guess I hyphenated earlier, doesn't matter. So a couple of rules of the road before we start. We're going to be talking in terms of A and B. A and B are in the set of positive real numbers, which just means it has to be, this just means A and B must be positive. That's all it says. Okay. Now, we're ready for rule number 1. If I have the log of a to the power of b, I can rewrite that as b times the log of a. That's potentially the biggest kind of moneymaker that we get just right off the bat. Why does this matter? We went into this with a problem, right? We said, okay, well, what if I have x in the power and I don't know how to solve for x when it's in the power, right? Then this rule says that, okay, if you have something in the power and you wrap a log around it, then you can rewrite it as the power downstairs, right? Kind of where you can solve for it times the log of a. Okay, so we're going to use, that's kind of the most important one. Okay. So here, right, this is how we bring a power, I'll say down. Oops. This is how we will bring a power down. Okay. So that's important. If I have a negative power, then it works the same way. Okay, so this one's kind of no surprise. So the log of a to the negative b is negative b times the log of a. Same thing, right? Just if it's in the power, it goes down in front. Okay. And so when would I have a negative power here, right? If this is a fraction, right, 1 over a to the b, right, then I could rewrite it first as a negative power and then bring that negative power downstairs, right? And so they're going to be kind of intertwined here. So recall a to the negative b is the same as 1 over a to the b. Okay, and this there. Okay. The third rule is, and we use this for kind of expanding or simplifying, and so we use it in any direction. All of these rules we often use in any direction. And so the log of a times b, you can rewrite as the log of a plus the log of b, right? So if you're multiplying inside, you can break it up into 2 logs, but you have to add them. Okay. Now I'm not writing the explanation down for these because at this point I feel like they're kind of obvious, right? We're more used to reading these things. And so similarly, and just because there's only one more log law, I am going to just give myself, oops, one more line. There. The fourth rule says that if I have division inside, right, and you can rearrange that division, right, a over b. I'll emphasize that it's division. Well, you have b to the negative 1, you can bring it all to one space, and then you can use rule number 3 to split them into addition, but then the addition turns into what? It turns into subtraction, right? So you can rework these rules and derive all these, but negative log of b. Okay. So only 4 rules for log laws. So that's easy enough to memorize. Okay. So for example, let's see here. Solve for x. If in 4 is equal to 3 to the power of x. Okay, it's our first one. And so now I see that I have an x in the power. So I need to solve for x. So first thing I'm going to do is I need to bring it downstairs. And so I'm going to use rule number 1, which brings that x downstairs. And so I'll rewrite it here. 4 is equal to 3 to the x. If I take the log of both sides, so the log of 4 is the log of 3 to the x. Okay. Take the log of both sides. Then I still have the log of 4, but that's equal to x times the log of 3. Okay. And this is from rule number 1. Like I said, we use that a lot, right? So now x is now available and I can solve for x. And so what I'm going to do is I'm going to do a little maneuver, right? I have to divide both sides by the log of 3. So I'm going to divide that over here. But then because I'm solving for x, I like to have it on the left-hand side. But x is equal to the log of 4 divided by the log of 3. Right? So now I know that x is the log of 4 over the log of 3. I can solve that. That is a number, right? The log of 4 on my calculator. How do I do it? Oops. Let's see here. I think I have to have 4 on my screen and then hit the LN button. Yeah. And then divided by, I'm going to use bracket 3 ln end bracket equals. So I'll use those brackets, or you can use the store function, right? Find the log of 4, store it, find the log of 3, store it, and then take those two and divide them. Just be really, really careful. Okay. Let's see here. So on the calculator, or maybe here. Whoa. Oh, it's doing it again. All right. X is roughly 1.261859507. The second button is for e to the x, right? So whenever you want that, those yellow functions that are above the buttons, you have to press the second button to get there. So on the calculator, the steps are like this. Let's see here. 4 ln. Okay. And then I use brackets. Oh, I forgot the division here. Divided by bracket 3 ln and bracket equals. Whew. Yeah. Okay. Okay. Good. So, let's see here. What if I want to solve? So for example 128, if you're interested, let's solve 3 plus y to the power of x equals 34 for x. Okay. So let's write this out here. 3 plus y to the power of x is 34. So immediately I see that I have this power here. So the first thing I'm going to do is I'm going to make sure that I can take the log of both sides, which I can here. And so the log of 3 plus y to the x is the log of 34. Now you want to be really, really careful that you're doing it on both sides. And this looks like a y, but it's an x. So now this becomes x times the log of 3 plus y is the log of 334. I'm solving for x, and I don't know what y is, so I won't be able to simplify any further, but that's okay. I get x is the log of 34 divided by the log of 3 plus y. And we can't simplify any further. Since we don't know why. We don't know why, the variable y. All right, once we know what that variable is, let's say y is 2, then we could take the log of 34 divided by the log of 5 and find a value. But for now, this is as close as we're going to be able to get for x. All right, I think that's good for today. So next week, we're finally going to start interest problems. So starting with simple interest. And then, like I said, everything's going to be very similar for the rest of the term. Hey, looks like the power's back on. No, just daylight. Oh, no, it's not on. And it looks empty. Anyways, if you have any questions, let me know, but I'll stop this recording. And I guess have a great weekend. Never see you guys. Thanks, guys.
Thank you, Prof.